So in the last video, we went over a number of different examples where VSEPR fails, but where we could use sort of a theory that's tacked on, another empirical theory that's tacked on to explain those results using sterics. We're going to go over now some other compounds that don't follow VSEPR and not for any steric reasons, okay? So the first one's strontium fluoride. So let's go through our VSEPR accounting scheme. Strontium is an alkaline earth metal, so we have two valence electrons, and then we have halides, the fluoride, two fluoride ligands, so 2 minus 2 times 1 is 0, so that gives us 0 divided by 2, 0 lone pairs. 2 ligands plus 0 lone pairs, that should be a linear geometry, so that should be linear, right? But experimentally, this molecule, strontium fluoride, is bent. It actually has an angle of 108 degrees, nothing even close to 180 degrees. And in fact, you can look at isoelectronic versions of analogs of this molecule, and any strontium halide or barium halide, VSEPR predicts that all these molecules would be linear, right? Because they're going to have the same steric geometry of 2 with 2 ligands and 0 lone pairs. And you can go and look at the experimental data, and you can see that 6 of these 8 molecules are actually bent. So 6 out of 8 times VSEPR gets it right. And then mysteriously for strontium bromide and strontium iodide, the molecules are actually linear. And so why is this? It's not entirely clear it's not at all clear using VSEPR. VSEPR offers no explanation, right? Let's do yttrium chloride. 3 electrons for yttrium. We have chloride, that's a halide, so it's a 1 electron ligand, 3 minus 3 times 1. Again, we're gonna have 0 lone pairs. This time we have 3 ligands plus 0 lone pairs. That should be trigonal planar. But experimentally, this is a pyramidal, trigonal pyramidal shape. And so, again, certain textbooks will tell you that, and this is indeed true, that SD orbital mixing occurs, and this is why VSEPR is failing here. But this explanation is beyond attack on theory. You've now invoked molecular orbital theory, right? And what you'll see in chapter 5, coming up soon, is that molecular orbital theory is based upon quantum mechanics. And so basically these examples, there's nothing you can do to fudge VSEPR theory to explain these results at all. And so for that reason, this really shows you a lot of the weaknesses with VSEPR theory, even in its purported strength, which is all about predicting structure, right? In chapter 5, we'll show how the spectroscopy of a lot of the molecules that you look at with VSEPR structures are completely wrong. But even where VSEPR is the strongest, it still has failings that cannot be remedied in any way. So, really just want to drive home this point because VSEPR is something that we all know and love. VSEPR is a rationalization. It's not an explanation. There's no underpinning theory. But you get the structure, or a structure, might not necessarily be correct, but a lot of times it is correct, right? You get it directly. We're going to be moving to using molecular orbital theory. This is a better approximation of the truth as we know it. And MO theory is based on quantum mechanics. The thing with MO theory is that it doesn't directly predict structure. So you can't run like abstract MO theory calculations on a given empirical formula, which is what you do in VSEPR, and then get out a structure. Instead, what you have to do is you have to test individual structures, okay, and look at their energies. And then what you're going to do is you're going to compare the relative energies of all these different structures, and whichever one is the most stable, i.e. has the lowest energy in the ground state, that is what MO theory predicts will be your ground state structure.